All right, welcome back to your favorite technical math class. Take a look at an introduction to functions. In mathematics, you can have a relation, which is just a correspondence between your input and output. Some examples of relations might be price of a gallon of gas and the price of a barrel of oil, right? And they don't necessarily have to be related either. You can make a relation with anything. But not all relations are functions. So in mathematics, a function is for every input, there's only one output. So how I like to remember that is for every x, there's only one y. For every x, there's only one y. And our domain is the set of all x values, or the set of all inputs. Our range refers to the set of all outputs, or y values. Now we have a graphical test to test if for every input there's only one output. And the graphical test is the vertical line test. So I just kind of wanted to introduce these functions to you initially, these relations, and see which one of these are functions, which one of these graphs are functions. So the vertical line test says for every input there's one output. So in other words, if I run a vertical line through, let's test like for an input of an x value of 1. For an input of the x value of 1, if I draw a vertical line through, oh my gosh. If I run a vertical line through for an x value of 1, it only hits once. In other words, for an x value, for an input of 1, there's only one y value. It only hits once. And it has to be anywhere on that graph. It can only hit once. See how anywhere on the graph that I tested, it's only going to hit once? Again, that means for every input, there's only one output for this graph. So yes, this is a function right here. Whereas the second one, if I test it, let's say I test it for an input of -2. See how there's two y's? There's two outputs there. So this is not a function. It fails the vertical line test. Again, the vertical line test says it can only hit once. Every time I run a vertical line through any part of the graph, it can only hit once. Notice over here I'm only hitting once every time. Even though it gets pretty steep, it still is increasing. So this, yes, is a function. So that's what a function is. Now what we have is function notation in mathematics, and that's just a nice way to express it in a concise manner. You know, mathematicians are lazy, not in the way that they don't want to work. They're very hard workers, but in the sense that they want to shorthand the notation whenever possible. And so that's what function notation does for you. So f of x is simply a nickname for y. So I have this example here. If you have, y equaling 2x minus 5. Function notation, f of x is just a nickname for y. F of x equals 2x minus 5. So instead of saying, hey, can you find the value of y when x is 3, you're just going to say find f of 3. Again, what that says is find the value of y or the functional value when x is 3. So you're just plugging in 3 for x. So you got 6 minus 5, which is 1. F of 3 is 1. Remember, f of 3 is just a nickname for y, right? Y is 1. So when x is 3, y is 1. When x is 3, y is 1, right? That's your function notation. It really comes into play with calculus quite a bit. It's very handy notation when you're doing derivatives and things as well. But let's go ahead and practice using the function notation here. So again, f of x is just a nickname for what? Y. So what is this saying? This is saying find y when x is -2. Find y when x is -2. So let's go ahead and write, here's our function, -2x squared plus 3x plus 1. When x is -2, let's go ahead and let x be -2 and find out what y is. Oops, that's a -2. So we got -2. -2 times -2 is a +4. 3 times -2 is a -6. So we got -8 minus 6 plus 1. -8 minus 6, -14 plus 1, -13. So f of -2 is -13. In other words, when x is -2, y ends up being -13. It gave us this point. right? But we're just trying to find that functional value, that y value. All right, for f of 0, we're going to go ahead and let x be 0. 0 squared is 0. 0 times negative 2 is 0. 0 times anything is 0. There's another 0 plus 1. So you should end up with a 1. F of 0 equals 1. In other words, that's the point when x is 0, y ends up being 1. All right? Gives us that point right there. And then finally for f of 3, you plug in f of 3. We've got f of x equals negative 2x squared plus 3x plus 1. Plug 3 in for x. And we got negative 2 times 3 squared. Well, 3 squared is 9. Negative 2 times 9, negative 18. 3 times 3 is 9. Negative 18 plus 9 is negative 9. Plus 1, I got negative 8. So f of 3 is negative 8. When x is 3, y is negative 8. All right? X is 3, y is negative 8. Now, there's different ways to ask this besides just with an equation. We could give you a table of values. So here's a table of values. Here's our x. Here's our y. In other words, our f of x. So if we have an input of 0, it outputs 69. If I have an input of 1, it outputs a 6, and so on. We just don't have the actual equation. But we can answer questions for it. So f of 2. So this is saying, remember, x is 2, right? If x is 2, what's our output? Mm-hmm. Perfect. When x is 2, it spits out 93. F of 5. Yeah, when x is 5, it spits out 12. Right? F of 5 equals 12. Now this one, C, is a little bit different. It's saying f of x is 6. F of x is 6. So this is saying the y value, right? My y value is 6. It's giving me the output. If the output is 6, the f of x is 6, then who's the input? Yeah, x would have to be 1, makes that true. In other words, f of 1 equals 6 is what this is saying, right? They're wanting the x value there. D, we've got an f of x is 14. So our output, f of x, is 14. What would x have to be? 8. Yeah, in other words, f of 8 equals 14. All right, that's what we're saying. All right, what's the domain? The domain of f, that's the set of all x values, right? Set of all x values is the domain. So if you're stating the domain, just put it in your braces here. So it's all these x values up top. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's your domain. That's your set of all inputs, set of all x values. Now your range, on the other hand, is set of all y values. All the y values, right, is the range of f. So in other words, f of x, it's all this outputs, all these outputs on the bottom. So you say 69, 6, 93, 43, 54, 12, 74, 2, 14, 13. Ideally, I'd put that in order, but I did state my range of that function, right? All the outputs. All right, so now we've got a graph on this example. This is a graph of g of x, function g. What would g of 5 be? G of 5. So you know normally it's g of x, right? So our x value here is 5. If we have an x value of 5, what's it spitting out? 3, yeah, so this point right there, right? When our x value is 5, see how it spits out a 3? So g of 5 is 3, right? G of negative 4, what would g of negative 4 be? Let's plug in -4. If I throw in a -4 for x, what's it spit out? What's the point? 2, that y value, right? G of -4 is 2. The y value, when x is -4, the y value is 2. Let's do one more, G of 4. What's our y value when x is 4? 0. Good. Right there. G of 4 is 0. All right, now this next one, this is the other way around. If g of x is 1, what's the x value? If g of x, in other words, if the y value is 1, g of x is y, right? Instead of f, we're using g here, g of x. If the g of x is 1, minus 2, good, yes. Here's that y value of 1. So the x value is -2. X must be -2. In other words, g of -2 is 1. Now there's actually 2 other spots on this graph where that is true. Here and here. I just don't know what they are. So we're going to ignore those for a minute. Right? But we do have some other y values of 1 on that graph, don't we? But we'll just go with the one that has a point there for now. All right, how about if g of x is -2? How about if g of x is -2? If the y value is -2. Yeah, if the y value is -2, 2, good. Yep, g of 2. G of 2 is -2. So again, x must be 2 to make that true. All right. And that's our little introduction to functions. Appreciate you guys taking notes. See you next time.